Hello. So today what we're going to talk about is a different type of differentiation than you've been doing in class. So the basic rules of differentiation that you've been using, your quotient rule, your product rule, chain rule, power rule, all that kind of fun stuff, has been what we called explicit differentiation. So we need this process called implicit differentiation to take the derivative of functions where we can't solve for y. So an example would be if you're given the function x squared y plus y squared x equals -2, and you want to know something about the rate of change of this function, or you want to be able to find a tangent line to it, you still need to take your derivative. How do you do that when you can't separate your y's and your x's from each other? So some things to know about implicit differentiation. The first thing you're always going to do is you're going to take the derivative of both sides of your equation with respect to x, unless the problem asks you to do it with respect to another variable. But usually it's respect to x, just like we always have been. So when you take the derivative of a term in your equation that just has x's in it, there are no other variables, you're good to go. You're going to use your basic differentiation rules, same as normal, nothing's going to change. But when we get to a term that has x's and y's mixed together, or any y's or other variables involved in that term other than x, we have to use the chain rule to take the derivative of it. So an example would be if we take the derivative with respect to x of y cubed, we're going to get 3y squared using our normal power rule, but then we also have to multiply that by dy dx, or the derivative of y with respect to x, because we don't know what the derivative of y with respect to x is. That's what we're solving for. We're solving for that first derivative. So some rules to follow for implicit differentiation now. So again, the first step you're going to do is always take the derivative of both sides of the equation. So you're going to do d dx, so derivative with respect to x. And then after you've taken your derivative, you have all your terms written out. What you're going to do is you're going to collect all the terms that are involving dy dx to one side of your equation, and you're going to move everything else to the other side. Because our goal here is to solve for the derivative, or that dy dx term, so we need to isolate that as a variable by itself. So once all your terms that have dy dx are on one side of the equation, you can factor dy dx out of all of those terms. And then you're going to solve for dy dx just like you would in any other algebra equation if you were solving for a variable. Okay, so let's do some example problems now and really see how this process gets used. So our first example is to find the derivative of y cubed plus y squared minus 5y minus x squared equals -4. So the first thing we're going to do is write out that derivative step. So we're going to go d dx of y cubed plus y squared minus 5y minus x squared equals d dx, or the derivative, of -4. So the nice thing about this first example problem is that we don't have any terms on either side of the equation where we have x's and y's that are mixed together. So we don't have to use any product rules or anything like that. We can just go straight through and use our chain rule to take our derivative. So the first term we're going to take the derivative of is y cubed. So the derivative of y cubed is going to be 3y squared using our power rule, but because we don't know what the derivative of y is, we have to multiply that by dy dx using our chain rule property. So moving on to the derivative of y squared, we're going to bring down that 2. So we're going to get 2y times dy dx. Do the same process with the -5y. So we're going to get -5 times dy dx. And then we get to that nice minus x squared term. So you're going to take the derivative of that term just like you have been. You're going to get that it's -2x equals the derivative of -4. 4 is just a constant. So we're just going to get a 0 there. Okay, so now we're going to group all of our terms that have dy dx's on one side of the equation. We'll move everything else to the other side. So that means these first 3 terms here are going to stay, and we're going to move this -2x over. So we're going to get 3y squared dy dx plus 2y dy dx minus 5 dy dx equals, moving that -2x over, we're going to get a +2x on the right-hand side. So now what we have to do is, since we want to solve for dy dx in the end, we need to get it by itself. So what we can do now is factor it away from everything, since it is a common element in all 3 of these terms. So we get dy dx times 3y squared plus 2y minus 5 equals 2x. And now we want to know what dy dx is equal to, so we need to isolate it, get it by itself. So what we can do is divide both sides by that quadratic term that it's attached to. So we're going to get 2x divided by 3y squared plus 2y minus 5. And that's going to be our first derivative of this function. So now you might be thinking, where did all those dy dx's come from? What happens if I forget to put them in? Well, if you forget to use your chain rule on those y's and don't have any dy dx's after you've taken the derivative, you'll eventually realize that you made a mistake somewhere, because when you go to solve for the derivative, you won't have anything to solve for, which will make things a little harder because you you won't have anything to solve for. What are you supposed to do with that? So whenever you take the derivative of y, make sure you throw in that dy dx term. And technically, we always do that even when we take the derivative of just an x term. So technically, when we did ddx of that negative x squared term, we used our power rule to get that it was negative 2x. But technically, we could multiply that by the derivative of x with respect to x. So that would be dx dx. But that's just negative 2x times 1, or negative 2x, which is why up until now we haven't really been considering the fact that technically whenever you take the derivative of something, you are using the chain rule. But since we are normally only taking the derivative of x terms with respect to x, the derivative of x with respect to x is always 1 because it's the same variable. Okay, so that was a fairly simple and straightforward example since we didn't have any x's and y terms mixing together. So now let's try an example where they do mix together. So that first function that was shown during this presentation, that x squared y plus y squared x equals negative 2. So again, we're going to start out writing our derivative out. So we're going to do d dx of x squared y plus y squared x equals the derivative, or d dx, of negative 2. So now the only issue that we have here is that we have, when we go to take the derivative of x squared y, that's x squared times y, or the product of x squared and y, which means that we have a product going on, which means we need to use our product rule. So just as a quick side note, we'll write out what that product rule is. So d dx of f times g equals f prime times g plus g prime times f, just to keep it straight in our heads. So I'm going to use parentheses to group the derivatives for first the x squared y term, which we'll do in red just to keep that straight. And then we'll do the derivative of y squared x in black, so it's easy to see which one is which. Okay, so going through that, using the product rule, we take the derivative of the first function. So that's the derivative of x squared, which is going to be 2x, and multiply that by the second function. We leave it alone. Add, and then we do the opposite. So we're going to leave the x squared alone, and then multiply that by the derivative of y, which is just going to be dy dx. So that's the derivative of our first term. So now we have to add on the derivative of the y squared x term. So following our product rule again, we're going to take the derivative of y squared, so that's going to be 2y dy dx, multiply that by x, and then we're going to take the derivative of x and multiply that by y squared. So we're going to get y squared times 1. And all of that set equal to the derivative of negative 2, but that's just 0 since it's a constant. So now we're going to go back to all blue ink, so it's all going to be the same color again. We're just going to rearrange some things and figure out how to find our derivative. So we said before that we want to group all of our dy dx terms on one side and move everything else to the other side. So that means that these two are going to stay where they are, and we're going to move the other two terms to the other side. So that means that on the left-hand side, we're going to be left with x squared dy dx plus 2xy, just rearranging the order of those letters, dy dx, equals, now we're going to move that 2xy term over, so we're going to get negative 2xy, and we're going to move the y squared term over, minus y squared. Okay, so now we want to solve for dy dx, so we should factor dy dx away from the left-hand side. So now we get dy dx times x squared plus 2xy equals negative 2xy minus y squared. And dividing by x squared plus 2xy, we're going to get that dy dx all by itself is equal to negative 2xy minus y squared, all divided by a positive 2xy plus x squared. just reversing the order of those terms. You can write the terms in any order, it doesn't matter, it's the same thing. So whenever you're doing implicit differentiation and you have x's and y's that are in the same term where they're all grouped together, you need to be careful that you're using any appropriate derivative rules. So like in this example, you might need to use your product rule, you might need quotient rule or chain rule, anything like that. But you need to make sure that you're always asking yourself when you're taking the derivative of each term, okay, what's going on between all these variables? What operation is there? Do I have a special derivative rule for that? Or can I just straight take the derivative with the power rule or something like that? Okay, so that's the end of this video. There is another video for implicit differentiation if you want to watch that, which is going to go over finding the second derivative of functions that use implicit differentiation and how to use implicit differentiation to find the equation of a tangent line. Okay, so thank you so much for watching. Have a great rest of your day.